It's the first time I came here for the DesignCon, and I think it's a very good experience for me. Important thing is you look at what other people do rather than just concentrate what you are doing. So you get a lot of insight from what other people do. It will inspire you to do something different.
I think it's a lot of, you can see a lot of focus, concentration on high-speed backplane. Like when I just joined with 10 gigabit is pretty fast. Today people are talking 120.
122.
I mean, I even see some at 400. That was a crazy data rate.
Yeah, I think it's good, right? When you go to the higher frequency, signal integrity is more important. So yeah, it's very important. Anything matters, like little wear, that matter too. How do you accurately model those effects? And that's also very important. Yeah, my presentation is about a frequency domain post-layout simulation for the printed circuit board. So the methodology basically is trying to make the board designer can extract the electrical parameter of the channel they've been working on before the tape out of the board, so they know their board performance before the tape out. So this one will require frequency domain S parameter extraction tools rather than the time domain simulator. The frequency domain CCT has three advantages. The first advantage is it's much efficient. It's 6 times faster than time domain simulator. And the second advantage is that we can handle the complex design, especially, for example, the PCIe server platform. You can have multiple boards like the main board and backplane and adding card. You can also have the connectors and cables and mux in your channel. So all the components can be cascaded in the frequency S parameter extraction. So the frequency domain method can extract the complex platform, so including all the components in the server platform for example, the PCIe Express bus.
You know, if you really look at the time domain versus the frequency domain, fundamentally they're the same. You know, the frequency domain can be converted to time domain. Time domain can be converted back to frequency domain, right? It's just one way, but it just so happens when you solve the Maxwell equation in frequency domain, in this particular case, it's much faster. So therefore, the frequency domain makes more sense in this particular case.
So I would say that when you're working with simulation tools, you should be able to predict the result before you really run the simulation. So simulation tool is really just for you to verify your prediction. So if you blindly use the simulation tool, and so you will not really get the insight of the SI. So you will make a lot of mistakes if you just blindly follow what the simulation tool tell you. So you should have the concept of the SI knowledge before you run the simulation.
Signal integrity is mainly about three things, right? It's a loss. When your signal goes through a media, a PCB, you get attenuated. Then the next important is reflection. You know, you try to reach from point A to point B. You want a signal goes, point B can receive it. But you don't want it all get reflected back. And the third one is noise, I just mentioned, coupling. So it's about those three things. I think most of the fundamental for all high-speed signals is impedance control, right? We usually want to control either 50 ohm or 85 ohm. You know, there is industry spec, you have to do it. The other important thing is to do impedance control, you need to have a reasonable reference, right? Reference plan. The other things you do is actually I think is really important. We often make a mistake. It's some critical signal get impacted by other signals, right? Like even the speed is not very high, you can cause trouble. Like even power, very low is power plant, and noise get to like a crystal. And then crystal fitting you to silicon, and everything is messed up. So those are very important.